The first thing I did was look at what we call a D-log, or a printout of all the data from the spacecraft. We had brought up another computing machine to just run what we call D-logs, into all the data and print it out once per second or once per minute, depending on the particular system that we wanted to look, the granularity we want to look at the data. And then, of course, the system I wanted to look at as soon as possible was the cryogenic system parameters. And I remember looking through because I still remember none of us had ever seen the pressure go up in O2 tank 2, because we were looking over here and it was happening over here. So by the time we looked back, there was no data there. It was just the readout of the parameters was as if the transducer or the gauge was broken, and it was not there anymore. The pressure in the tank had gotten over 1,000 psi and blown the top of it off. As you probably know by this time, a sheet of hot gas flame went up, knocked the top of the tank off and hit the upper shelf where the fuel cells were, and blasted onto the fuel cells and blew that particular service module segment out into space, which is a good thing it did that. If that, by the way, as an aside, if that panel on the service module had blown when it did, there was a good possibility that the pressure could have built up in, if I can show you this, the pressure could have built up in between the command module and service module. They were held together with 3 frangible struts, or tension ties we call them. And the force of that explosion could have accumulated pressure in here and broken the 3 tension ties. So the command module would have been hanging like this by its umbilical. That would have really been bad. Now it's really exposed to deep space, the aft heat shield. Fortunately, it didn't happen. When the explosion occurred and we pretty much figured out what had happened, we didn't know exactly what happened. All we knew were the end effects, where we knew we had lost 2 of the 3 fuel cells. As we know now, the force of the explosion against the upper shelf, where the fuel cells are located, slammed shut the supply valves to the fuel cells, and within 20 seconds, those 2 were dead. That's all it took. So rapid action wouldn't have helped there. I mean, it was too quick. It effectively starved to death. And one of the things we were doing post-explosion was trying to deduce where the problem was. And we thought maybe the problem was with the fuel cells. We got pretty close, it turns out. We thought there had to be a leak common to everything. And as it turns out, there was a leak common to everything. We didn't know exactly where it was, and we couldn't do anything about it. We had, when I asked my backroom guys how much time we had on that remaining oxygen tank, which was coming down, there was only about 320 psi left in it of the 900 it normally used to operate at. We had 1 hour and 54 minutes of life left. So we had 1 hour and 54 minutes to do something orderly. And the ultimate orderly thing was to get into the LEM and live there and shut down the command module in an orderly fashion and then get into the LEM. So my time personally was being occupied with still trying to figure out what the problem really was and what it meant to the life. Was there anything we could salvage out of the command module? It turned out the answer was no. The failure occurred the last hour of my shift. And the interesting thing is, if I hadn't asked for the extra stir, then my colleague EECOM, Clint Burton, would have asked for the stir when the crew got up in the morning, and that would have happened there anyway. So it was either I did it or he did it. It would have been separated by 8 hours. So my job at that point was to continue deducing what the cause was. Finally, after about 20 minutes or so, we knew what the end result was, and that was the command module was going to be dead in 1 hour and 54 minutes. So about that time, I recommended we get in the LEM, and we started the orderly procedure of powering down the command module and leaving it in a known configuration and powering up the LEM. And that's what the next shift did after that 1 hour period of mine. according to what we found was this failure had been building for about 5 years. And the the way the hardware is built up is that these two oxygen cryogenic tanks are built onto a wedge-shaped segment as a kind of a subsystem. And at the factory, it was Beach, I guess in Boulder, Colorado, apparently it dropped a short distance to the floor when they were transporting it. It wasn't a great distance. But at the same time, and normally it wouldn't have made any difference, but at the same time, one of the tubing runs that was used to fill and drain the tank, the joints were made to max tolerance so that they became shock sensitive. And apparently the jolt on the tank when it hit the floor caused the tubing to misalign in such a way that it obstructed flow. So this tank set was shipped to Rockwell to be installed in the service module. The technician who was running the control panel on the ground at the Cape we'd finished the test, as I remember, and we had to empty the tanks. Well, normally the heaters would empty the tanks, the normal heaters would. And the tank wasn't emptying very quickly. This was O2 tank 2. So the technician turned the heaters on and left them on. His instructions were not to let the temperature of the tank, the internal temperature of the tank, get over 80 degrees Fahrenheit. These heaters were changed to operate from 67 volts DC to 28 volts DC, and the thermostats that would open up when the temperature got so high and would shut the heaters off were only rated for 28 volts DC, and the current did that correspond to that. Well, the ground console was capable of delivering 67 volts DC. That means a lot greater amperage, and it fused the thermostat shut. Now you have no protection to shut the heater off for over temperature. So we have no protection, and he's told not to let the gauge get over 80 degrees Fahrenheit. He's reading out the temperature in the tank. Unfortunately, he doesn't realize or let himself realize that the gauge only goes to 80 degrees Fahrenheit. So it sat there pegged full scale at 80 for a number of hours, and the temperature in the tank got much higher than just 80 degrees Fahrenheit. It got up high enough, it's felt, to char the Teflon coating of the heater and fan wiring, and just let them bear. And post-mission testing duplicated that very thing. So it was just a matter of time before normal dynamics on the system, maybe a little slosh, caused more of the insulation that was virtually gone anyway to move away and allow the wires to really touch and short out the circuit. Even with the charring of and embrittlement of the Teflon wiring, that Teflon represented enough hydrocarbons in the tank with that massive amount of cryogenic oxygen to create an incredible, massive fire in the tank, which is exactly what happened and blew the top of the tank off. The explosion happening in any other time of the mission than when it did probably would have been a lot more critical. It wouldn't have happened earlier necessarily because we were only a couple days out. And remember I mentioned that we stirred the cryos post-sleep. And I think this is like the second post-sleep period. Or I think we only had one sleep period at 54 hours into the mission. And later on, the later it happened, the worse it could have been. The earlier it happened, the better it is, obviously. Later on, put it this way, if it happened in Earth orbit, it'd been better. It'd been the best of all. But since we had done the translunar injection burn, we're already on way to the moon, and committed, the later it happened, the worse it could have been. The worst time it could have happened, of course, is when we had separated the LEM from the command module, and we had gone down the moon, and we would not have had the lunar module consumables that was in the descent stage available to us, and they would not have made it back then. It happened early enough where we could do we had time to figure out whether we wanted to do a free return around the moon or abort immediately. We had more time to work with, and it's been said before, this is probably one of the best times it could have happened. If that failure had occurred today with the shuttle, I mean, it wouldn't have been missed, because with the shuttle, we know every switch position on that spacecraft on the ground. We have the redundancy is sometimes 5 deep. So, and the lessons we learned from the Apollo 13 accident were incorporated into the design of the shuttle. So that the lessons there were not for naught at all.